James Ray, but I won't. I will be above that. James Ray is here as well, and I thank him for his support and his scientific expertise in so many ways, especially in reviewing a lot of the translational medicine proposals that come through. We welcome you to the Plenary I session again. This is the second one since we all had to kind of go away for a little bit. Nice to see everybody back here and comfortable, and we wish you well. Next slide. So here's our lineup for today. I'll give a couple minutes of introductory comments and throw out a couple ideas. Then we usually start off with an awardee from the Hope Foundation, and today we have the pleasure of hearing from Kim Blenman from Yale, who is a recipient of a Coleman Fellow Award. We also have highlighted translational medicine within each individual disease site committee, and I think this is important because maybe there'll be cross-fertilization. One thing that one committee is doing, another committee could pick up on or do this in collaboration. And then we usually have a translational medicine talk, and today we're going to change that a little bit. This relates to translational medicine, but I think there are certain areas that we need to get into, which includes AI, artificial intelligence, and always when I don't know something about a topic, I like to have a speaker come and talk on that because I assume there's a lot of people who don't know about a certain topic. And I will introduce a concept that maybe we even need to have a workshop on some of these newer concepts that come forward in translational medicine and cancer research in general. I'll come to that at the end of my opening comments. So we have a great lineup today. It would be an hour and a half, and then I know we have more committee meetings coming up. This is important, presenter disclosures. Of course, we always want to be honest and work with integrity. I'm sorry, I did not forward that. This should stay up here. I was actually going to make a point that too many times at meetings, people leave this up here for about 0.6 seconds. That's not long enough to read the relevant disclosures, so we will leave this up here for another 6 seconds so you can read through it. And I hope you were able to read everything, and now we will move on. I'm not sure if this advancer is working well. Can you go back one slide? I want to make sure I didn't miss anything here. Okay. So, as always, we thank the Hope Foundation for their support in so many initiatives in cancer research that ultimately impact our patients. So here are upcoming funding opportunities from the Hope Foundation, which you can find on their website. You see the SEED Award coming up soon, December 1st, up on the left. The next deadline is January 15th for the SWOG Hope Foundation Impact Award. You'll see several folks in the audience who have received the Coleman Fellowship, including Kim, as I just mentioned. Those applications come up in the first quarter of next year. And the SWOG Career Engagement Award, likewise, that application is due March 1st. So wonderful opportunities from the Hope Foundation. And recent funding of awards, as I just mentioned, Kim Blenman, our first speaker, has received the Coleman Fellowship. Jonathan Sham from the Hutch has also received a Coleman Fellowship, and you can read the interesting research that they're doing and the titles of their awards. Other awards, Abdul Rafe Nakash, if I said that right. If I didn't, my apologies. Has a Impact Award from the Hope Foundation and SWOG, and Jens Reuter and Meghna Trivedi have SWOG trial support. And again, if I said that wrong, my apologies. I'm doing my best with the slides that I have been provided with. So we thank the Hope Foundation for just support of so many initiatives that impact not only our investigators, but downstream impact our patients. And that's why we are here, to impact the patients that we care for. So thank you, Hope Foundation, and all the donors to the Hope Foundation as well. So let's look to the future. We've had lots of these translational medicine symposium, and typically, as I mentioned, I would have a translational medicine talk as the third talk on one topic or another that I think is relevant, mostly immuno-oncology recently. But I start to wonder, there are areas that we need to dive deeper into. So should we consider at the next SWOG meeting, let's say Thursday earlier in the day, a rapid, perhaps 1 hour session of rapid 10-minute talks on a topic such as artificial intelligence or omics platforms. And for the next meeting, since we're having an AI talk today, I thought that we could start off the next meeting, if you for James Ray about your thoughts about this, to have a mini symposium, really start to learn what the companies can do. And this is not a CME symposium. This is to teach us what the companies can provide in regards to support and technology, et cetera. And then you'd be able to meet with them at exhibits and talk with them about the projects that you have and interact and start a collaboration with them. So provide feedback mostly to James Ray, but if you find me, you can provide feedback to me too. So let's move on to the first talk. We're pleased to have Coltman Fellow, Kim Blandman, will talk about image analysis-based TILS measurement, predicts breast cancer PCR in SWOG 0800. Kim, please. In SWOG 0800 neoadjuvant chemotherapy trial. So thank you, and we hope you enjoy this afternoon's program.
Okay, can everyone hear me? Okay, great. Fantastic. First and foremost, I'd like to thank the organizers for inviting me to share how image analysis-based TILS measurement predicts breast cancer PCR and the SWOG S0800 neoadjuvant chemotherapy trial. So I hope I can get this working. Fantastic. So this is a phase 2 study of bevacizumab, which is an anti-VEGF inhibitor, versus standard of care chemotherapy in patients with HER2 negative, locally advanced breast cancer, LABC, or inflammatory breast cancer, IBC. The pathological complete response, or PCR, okay, there we go. In the study was most significant, was higher in the bevacizumab arm than the control chemotherapy arm. And this was actually a response to the results from the triple negative breast cancer subtype. But there was also a nice trend in IBC and hormone positive subtypes as well that led to this result. So this actually inspired us to think about what type of predictors or very simple predictors can we use to distinguish those patients who are going to respond and those who are not. And so at the time we were thinking about tumor infiltrating lymphocytes. And as you know, tumor infiltrating lymphocytes are prognostic and chemotherapy predictors in a host of different cancers. So TILs are predictive of higher PCR rates and are associated with better survival of breast cancers in general. So a very simple measurement of TILs is to do manual stromal TILs score, which is defined as the percentage of tumor stromal area occupied by mononuclear immune cells and H&E stain slides. So we examined the association of manual S-TIL score with PCR, event-free survival, and overall survival in the SWOG S0800 cases. And so in general, what we found was that using the manual S-TIL score as a continuous variable or separating into quartiles for percentage and categories, that there was actually a nice weak association with PCR. However, we did not find any correlation with event-free survival or overall survival. So this actually begged the question of how good are we really at manual TILs scoring? So we recently published a trial where we actually compared individuals who were pathologists who were experts at TILs assessment with pathologists who were non-experts. And so that's what we call our crowd case. And In the first set, we had 29 pathologists score 640 regions of interest. And as you can see from this data, there is actually significant variability in the scores. And then we actually took, we actually took a smaller set of pathologists, 7, who were non-experts, and compared those to 8 experts. And what you can see is that across the board, just roughly in terms of variance or variability in the scoring, that the crowd or the individuals who were non-experts, the variance were at least 3.5 times greater than those of the experts. But I also want to point out that in the expert evaluations, that there's also appreciable amount of variability. So what have we learned? So there is an association between manual STIL score and PCR. We can leverage simple H&E slides and manual STIL score to predict PCR and survival. But what are the gaps? So we have found, and also in the literature, that manual STIL scoring is labor intensive. The scores between pathologists on the same slides have high variability, and this is just because, just in general, we as human beings are not good at counting objects in high complexity environments such as the tumor immune microenvironment. And so this has resulted in the clinical adoption of STIL scoring to be hindered by the amount of time required for scoring and the variability between scores. So how can we help pathologists to literally reduce the amount of time that they spend doing this task and to decrease the amount of variance of the results that they produce? And so one method is potentially through doing digital TIL scoring. So there are actually quite a number of hardware and corresponding software platforms that have been developed to literally quantify objects such as TILs in the microenvironment of tissues, okay? And so our question was, can we create an image analysis-based TILs measurement that predicts breast cancer PCR at least as good as a manual STIL score? So our data set was the 113 pretreatment cases from the SWOG S0800 neoadjuvant chemotherapy trial. We used QPath software and the convolution and an algorithm that consisted of a convolution neural network, cell classifier CNN11, to create an EAS TILs percent as the digital metric of the TIL score, defined as the sum of TILs area over the stromal area times 100%. And so here I show the demographics. So this is the original SWOG S0800 trial with 211 subjects. And this is the subgroup for the digital trial analysis. And what you can see is that there's really no difference in the population, right? And so I also wanted to share with you just a representative image of the H&E stain images with the corresponding TILs, digital TILs classification. So on the right-hand side of that panel, you can see that the classified cells, the tumor cells are in red, the TILs are in purple. Wow, sorry about that. The fibroblasts are in green, and the other cells are actually in yellow. Okay, there we go. So on the left-hand side are the digital TILs results, and on the right-hand side are the manual TILs results. And so as you see here, the overall PCR is associated with high TILs score. And what is interesting is that the digital TILs tend to yield more significant p-values that you see on the left panel when we compare between PCR and residual disease. And then when we actually look at the different treatment modalities, so chemotherapy versus bevacizumab, we can see that the bevacizumab arm shows actually, again, the same trend where the PCR is associated with higher TILs compared to those patients who have residual disease. And once again, the digital TILs yielded more significant p-value results. And interesting, there was really no statistically significant difference within the chemotherapy alone arm. So the PCR rates are significantly higher with bevacizumab in patients with high TILs pretreatment, with EAS, with the digital TILs yielding more, again, more significant values. And again, we didn't see very much in the chemotherapy alone. So the manual TILs and the digital TILs scores are highly correlated. The receiver operating characteristics curves show that the digital TILs percent is potentially a better predictor of response than manual TIL scoring. And so what have we learned? So we observed strong positive correlation between the digital TILs and the manual TILs. The area under the curve, ROC curve, was higher for the digital TILs than the manual TILs. And then, so in general, the digital TILs quantification is predictive of PCR in breast cancer and have better response discrimination than the manual S-TILs. So where do we go from here? So there is very little information about the interactions, or if you will, the spatial dynamics of the components of the tumor immune microenvironment. So spatial dynamic proximity metrics, such as the Morishita Horn Similarity Index to measure the extent of the colocalization between cells, and the things like the cell-cell contact score are things that can be used to tease out, the interactions. And so our hypothesis is that the immune cell, cancer cell spatial proximity predicts for PCR to chemotherapy in the SWOG S0800 clinical trial, just like the TILS metric. So what are our next steps? So first, we will develop an image analysis tool that can quantify immune cell, cancer cell spatial proximity. We will determine if spatial dynamics expressed as the cell proximity and cell-cell contact are associated with PCR and or event-free survival. The tool will consist of multiple spatial proximity measures. And then second, we will validate the predictor. So that is the image analysis tool that we create. In the Yale investigator-initiated neoadjuvant durvalumab trial, which is an anti-PD-L1 inhibitor that's given in conjunction with standard care chemotherapy for the tools association with PCR. So what is our long-term vision? So our long-term vision is really to develop and validate a tool to measure the spatial proximity of immune cells to cancer cells using scanned images of H&E slides. So that's, low threshold. And then we'd like to potentially use that tool in a large randomized trial to test the hypothesis that close immune cell, cancer cell proximity in residual disease tissues is predictive of selective benefit for adjuvant pembrolizumab therapy. So with that in mind, I'd like to just mention to the audience that there are a lot of artificial intelligence and machine learning, including deep learning tools that are being created. So there's a lot in the pipeline for the field that we call digital pathology now. And so we have to have a method or a process to verify and validate the algorithm performance. So I have a collaboration with the FDA to create a high quality validation data set, which includes images, slides, and pathologist annotations that will be provided along with a statistical software package for data analysis to algorithm developers for validation of their algorithms' performances for TILS assessment and submission to the FDA. And so I'd like to extend an invitation to any pathologist in the audience who's interested in helping with this annotation to please contact me. So I'd like to close in acknowledging the members of my research team, specifically Yihan Liu and Shuting Wang. I'd like to also acknowledge the biostatistic help from Dr. Wei Wei. I'd like to do a special acknowledgement and thank you to Dr. Yulai Bai for actually creating the algorithm in Dr. David Rim's research group. I'd also like to give a special thank you to Dr. Lajos Pushtai and his clinical fellow, Dr. Christina Ferrucci, as well as a special thanks to Dr. Bill Barlow for his statistical support. And then in terms of funding, I'd really appreciate and want to thank the Hope Foundation for Cancer Research for the Cultman Fellowship. And last but not least, I'd like to thank the patients who participated in this clinical trial. Thank you.
Thank you. Can you hear me? Yes, you can hear me. Okay. We have time for 2 quick questions. Obviously, I love the fact that you're already planning the validation study in a very precise manner. Can you identify another clinical trial where you can test this hypothesis and do an exploratory analysis and a validation set on the same samples at the same time to keep things moving?
That's an interesting question. So I think what we will actually do is to take advantage of some of our data sets at Yale, and then we can talk a little bit more about, other data sets that we can take advantage of. So that's a great question. Absolutely.
I always love biomarkers that predict outcome. You did show a correlation with the PCR, but as you said, I think the PCR didn't correlate with survival. Did you try to see if the TIL measurement correlated with a waterfall plot or something like that?
Yeah, so it's interesting. So at that point, so the limitation with this particular data set is that we only had 3-year survival, and that had very few, events. And so I think that was the reason why we didn't get, the results that we were anticipating. So as we get more mature, data sets, we'll be able to get a little bit more information. I think it'll pan out the way that I think that it should, in terms of having an effect on those event-free survivals and overall survival. Okay, thank you very much.
That's outstanding work, and thank you to the Hope Foundation as well. Our next speaker is Phil Mack, and I always think of Phil as a Californian native, but Phil, of course, has moved to the East Coast now, and of course, you see his current affiliation at the Tisch Cancer Institute. So, Phil, thank you for joining us, and we look forward to your talk. Can you please set the clock to 15 minutes, please?
15 minutes. Okay, well, thank you very much. Thank you all for attending the plenary sessions, which I think are very important components of SWOG. And on behalf of the Lung Committee, I'd like to give you an update on some of our translational medicine endeavors. And because we haven't given a talk before at this meeting, I thought I'd spend just a few slides to talk about what our committee is really about, what some of our goals and aspirations are. And then I'll end with some more specific science in detail. So our strategies for the TM committee and the Lung Committee as a whole really are to maximize the information gained from each clinical trial, which may strike you as an obvious truism, but the very pertinent counter argument to that is that if you try to ask too many questions in a clinical trial, you're just going to end up diluting your results. It can be a dangerous thing to do. So I bring this here to you as from a TM perspective, and I'll show you in the next few slides what we mean by that. Secondly, in lung cancer, we have a plethora of agents for a wide variety of segments of patients, but we're always looking for ways to increase our predictability of how agents should be employed, not just these one-to-one relationships between EGFR or ALK, but looking for cofactors and other information from biologic information that might allow us to refine our algorithms and even subset patients even further, even though currently they may only represent 2 or 3% of the population, to really maximize their benefit. Finally, we were pretty early adopters of plasma analysis, particularly circulating tumor DNA, and we've built this into a lot of our trials over the years, and I'll talk about that in detail. So if the Lung Translational Medicine Committee were to have something as banal as a mantra, it would read something like this: not every clinical trial changes patient care, but every clinical trial is a learning opportunity. Again, this strikes me as a truism, but in many cases, we often fail to realize this endeavor. Let me give you some examples of this. So one of the very first studies I worked on in SWOG was this older trial, S0003. And this was a randomized phase 3 trial of chemotherapy plus or minus this agent, tirapazamine. And unfortunately, this agent was just way too clever for its own good. It did not work. You can just focus on the red highlights there. It was pretty clever, though. It was supposedly a bioreductive agent that would become a free radical in the presence of hypoxia, for instance, in the center of a tumor, and it should be tumor specific. It just ended up being very toxic and not particularly efficacious. And that was published in the Journal of Clinical Oncology, the outcomes. But this also provided an opportunity. And the opportunity was that we prospectively incorporated plasma kinetics into this trial, even at such an early date. We were looking specifically for circulating markers of hypoxia. And so with that information, we were actually able to generate a second paper published also in JCO based on our findings of the prognostic effects of osteopontin. And I was also particularly interested in the pharmacodynamic effects that we were observing continuously in our patients, particularly with VEGF and PI1. It was very intriguing. But that's not where it ended. We also used this study as a backbone for common arm analysis. And what we mean by the common arm analysis is a mention of Dr. Gander and I think John Crowley at the time, is that one of the burning questions was, why do Japanese patients receiving chemotherapy seem to have better efficacy but much higher toxicity? It could be due to the population, or it could be that they use different drugs, different agents, and different schedules. We weren't able to ascertain that from the literature, so we set up this common arm where we used the chemotherapy arm of this study in relation to two Japanese studies where they used the exact same regimen in a completely standardized way to determine whether these differences were biological or clinical. And to make a long story short, we did in fact find that the improved efficacy and higher toxicity that are experienced by the Japanese patients still existed even when you standardize for everything: dosing, drug type, drugs, class, schedules, everything. But it led us to further examine potential genomic markers that might actually predict for this, particularly things involved in paclitaxel metabolism and DNA repair. And we found very significant differences between the two populations, but nothing that we can really pin our hat on as to why they're experiencing these differences. But nevertheless, for a trial that had a very negative outcome, we were able to generate 3 publications from it in JCO. And that's kind of what I mean by maximizing the information we get from each clinical trial. Another example is our fascination in the committee, really, in retrospect, more of a fixation with EGFR monoclonal antibodies in lung cancer. We've done a lot of analysis of this. Preclinical models always suggest that it should be a really good combination, but the clinical trials have always been sort of moderate. We set the stage early with this with 2 early trials, the 342 and the 536, which gave us some preliminary data, but also allowed us to really refine our tools. In this case, EGFR FISH and other things that were developed in Fred Hirsch's shop in Colorado. And this led to the seminal study 0819, which was a large randomized study in this area. And I bring this to your attention during the TM committee, because I really like the trial design. This is from Mary Redmond here, where we actually had co-primary endpoints looking at all comers, but also focused on a specific subset of patients that we thought would receive maximum benefit. In this case, the EGFR FISH positive subgroup. But this didn't interfere with trial accrual, because we would determine this after they were enrolled, and we just had a goal of meeting both buckets of the populations. So it didn't delay entry into the study, and that was published by Roy Herbst in Lancet. But we were able to follow up on this with more detailed algorithms, because we did a lot of additional work on this. And without getting too much into it, what we were able to find was that we are still seeing this modest but significant overall survival benefit from the addition of cetuximab, in this case, to chemotherapy in a squamous cell population that was positive for our biomarkers. And we were able to actually enhance this a little bit and develop newer algorithms. So if anybody really wants to take some new gambit, haven't learned the lessons about monoclonal antibodies, and want to try this in squamous cell carcinoma, we actually have the algorithms and the tools all set up to do this. And additionally, we also saw that there was no impact whatsoever from KRAS. This is very different from colorectal, where KRAS is very predictive of outcome. In lung cancer, definitively in this phase 3 trial, randomized, we were able to determine that in the adenocarcinoma group, KRAS just has no effect. But of course, no patients were really benefiting. And that was published recently as well. So I would be remiss a little bit in giving a lung cancer update if I didn't talk at least briefly about LungMap, our seminal study, which is very TM oriented. I'm not going to go into too much detail about this because Roy Herbst tomorrow will be giving a large overview in the plenary specifically focused on LungMap. But just from the TM perspective, if you're not familiar with the study, many of you are, but if you're not, here the design is that we take all the patients that want to enroll on it and do comprehensive next generation sequencing just up front, every single patient. And then if they are positive for a particular biomarker interest, they are assigned to a sub-study that is relevant for that population. And we have this rolling barrage of continuous sub-studies that are always being newly approved. And if they don't have a biomarker that matches the sub-study, they have the option of joining or enrolling into a non-match sub-study. And I bring this to your attention from a TM point of view because as the map shows, this accrues from all across the country, with 50% of the accrual coming from community sites. And we have quite a large number of patients represented here in this study, a large number of specimens that have been banked even after the next generation sequencing, including a lot of plasma, which we made sure to include on all of these. And it's a very real world population. Again, 50% accrual from community sites. So it really actually has turned more from a clinical trial into a clinical resource. And we're just starting to tap into that for translational medicine components on a sort of a multi-level way. And what I mean by that is many of the sub-studies actually have their own TM components that are specific to those agents. But we had this large resource with all of these, this patient data that's already been generated. And we're using that to look at a number of different concepts. And again, I won't go into the detail here, but looking at tumor mutation burdens through different mechanisms to see if we can tease out better predictive models there, doing a lot of hierarchical clustering and analysis to identify interesting factors and subpopulations. And of course, we've been working on generating some comparison analysis between plasma and tissue, since we have that in a lot, just to see whether in the future we can use ctDNA as an entry criteria. And we're looking at that in a lot of depth. So that's pretty interesting. So what I really want to bring your attention to, and we'll focus a little more into the science here, is some of our analysis with ctDNA, a lot of which was embedded in the S1403 study. This was a study, as you can see from the title of the final article in the JCO, of afatinib with or without cetuximab. Again, we're obsessed with monoclonal antibodies. And there was actually no improvement on a clinical level from the addition of cetuximab to afatinib. But every clinical trial represents a highly annotated group of very similar patients that are treated concordantly, where we have great follow-up. And you can always learn a lot from your clinical trials. And so even though the primary endpoint was negative, I'd like to walk through some of the stuff that we've actually learned from this study. And again, here we prospectively incorporated serial liquid biopsy analysis, specifically looking at ctDNA kinetics over time. And this was very recently published in Clinical Cancer Research. So basically, this is what we're seeing on this patient set. If you just look at that graphic, we managed to have 81 patients from this trial where we had all 3 time points. We gathered 3 time points, a baseline, end of cycle 2, which is 8 weeks in, and then at progression. And these are just graphed here in buckets. It's not a time course. But you can see a lot of these patients went through the same kinetics, which is that if they started out positive, they would dramatically reduce their levels at that first time point, and then at progression, they would come up again, kind of this V-shaped curve. Now, not every patient has detectable EGFR at the get-go. Bear in mind that this is a trial where that was first line, they weren't treated with anything else. They're EGFR mutant, which is less genomic stability in general, so it's hard to detect. We actually saw a 77% detection rate at baseline. And this leads to 2 questions. When you think about this kinetics, and you think about the number of patients here that actually quote unquote cleared, which is to say they started positive and then became negative at that first time point, what can this tell us about the predictive capacity of ctDNA kinetics at that early time point? And what does it mean, if anything, to be baseline negative? Is that a prognostic factor? Obviously, it must be a good thing probably, right, to not shed ctDNA if you have a tumor, even though it doesn't give you any predictive information. So we'll take a look at much more detail at those plasma curves. And here we broke them up into ones that cleared completely. In other words, were reduced to below the level of detection. Those are color-coded here blue. The red ones are ones that had residual ctDNA EGFR mutant detectable at that first time point. And here on the log scale, you can see quite clearly the difference between those blue and the red. And of course, we have more patients on here than the graph I just showed, because here we were able to log in everybody where we had both a baseline and a cycle 3. But you can see in the afterwards, looking at the time course and progression, those patients that failed to clear, that had residual ctDNA, you can see had really rapid progressions, increased their ctDNA levels really quickly compared to a lot of the patients where the ctDNA cleared away, the blue ones. And so how did that translate into actual survival curves? Well, the Kaplan-Meiers were quite actually pretty impressive here. With a hazard ratio of 0.23, clearance of ctDNA was very predictive of long-term outcome. You can actually see that the progression-free survival was 3 times longer for patients who cleared their ctDNA than those that didn't. And those that didn't often had dismal outcomes, especially considering that they're EGFR mutant and they're being treated with an EGFR inhibitor. And this held true for overall survival as well, with a hazard ratio of 0.44. And you can see, hopefully, the distinction there in the survival curves. So actually, patients who cleared their ctDNA had twice the overall survival of patients who didn't. There's a lot of additional information that we can gather from this study as well. So I should emphasize that what we're looking at here is not a pharmacodynamic effect of EGFR. It's not that we're looking at EGFR mutants we expect them to clear because we're being treated with an EGFR inhibitor. This is just an effect of essentially tumor burden shedding. When you're treated with an effective therapy, whether they're put into a cytotoxic state and killed or they're put into a cytostatic state, you are reducing the amount that is being shed, and that is a good prognostic event. You can do this actually with any marker. We happen to be in a favorable situation where we knew that all of these patients were EGFR mutant. We had the tumor, we even did central confirmation of the EGFR. The plasma matched perfectly in every single case. But you could do this with P53, as I'm showing you here. You know, they go through the same kinetics, and you can actually derive statistical value from these. But in this case, you know, not every patient has a P53 mutation, and it's difficult to interpret the baseline because we don't know whether it's supposed to be there or not. So it's not as utilitarian as following EGFR, but I just wanted to make the point that it still works. Another finding that was surprising to a number of people, although not to me, was that plasma clearance actually dramatically outperformed RECIST monitoring for predicting long-term survival. And I'd be happy to discuss that with anybody who thinks that isn't an odd finding. But here I've graphed out the effects of essentially whether you had a response or not by RECIST. And you can see it really was not predictive of progression-free survival, and was only poorly predictive of overall survival. And again, this is a cohort of patients who are treated with EGFR, and they all have EGFR mutants. So many of them are responding, they just don't have great durable responses. And that's what the plasma is telling us. So also, we tried some more advanced algorithms, particularly partnering with Guardant here, to look to see whether one of their molecular response analysis, or essentially a consensus analysis of all of the ctDNA that's out there, is a better predictor than just following the EGFR mutation. And it turns out, at least in this specific subset, that just looking at EGFR mutations was more predictive. Although the molecular response looked pretty good, you can see there, at least for the progression-free survival, trending for the overall survival. It's a good algorithm. But in this specific case, where we have a specific driver in a specific population, following just that simple driver may actually be better. Why? Because of residual contamination that we constantly see from clonal hematopoiesis, which is a much bigger deal than we thought when we first entered into the plasma analysis space. Maybe as many as 25% of patients actually have some non-tumor mutations in circulation. And this study incidentally made it very easy to sort those out because the CHIP ones do not respond in that V-state fashion. They just kind of stay straight. They're not being affected by the EGFR inhibitors. And so it really became very clear what was CHIP and what isn't in this particular study. And then finally, just a quick word on amplification. Amplification is measured in these assays as an orthogonal approach, so unrelated to the actual mutant allele frequency. And many of you get your plasma analysis back from your favorite companies, and you see all these amplification events, and you're really not sure how to interpret them or whether you really should interpret them. But at least here for EGFR, where we know about 30% of EGFR mutants are also amplified, we saw an extremely strong relationship between the mutant allele frequency and the determination of amplification. And this really accounts for why we have some of these baseline readings of untreated patients having MAFs in the 60s and the 80%. It's because they're amplified. And that's not true of all the tumor markers, it's just true of the amplified EGFR. So in this sense, it read very realistically in terms of what we expected to see in terms of application. It's always nice to see what you expect to see. And I mentioned, and I know I'm over time, but that we would go back to talk about baseline findings. So what about that 23% of patients where we just didn't even see EGFR in the ctDNA? It was just not present in the blood. Bearing in mind, again, that all these patients we know to be tumor positive. EGFR, in this case, 77% of them were detectable at baseline. And there was no association between baseline positivity and just basic demographics, with the exception of an interesting association with age, where younger patients were more likely to be baseline positive. It's something I'd be eager to discuss with anybody. But what we did find is that there was a very significant association with M classification, whether the M1A or M1B, how extensive their metastases is, where M1As, only 60% were detectable, but 89% of the M1Bs were detectable. We also saw significant relationships with the location of the metastases. Liver mets were universally detectable in this study. If you have a liver met, then you have ctDNA, in comparison to those without liver mets, where it's only at 71%. And brain mets were also more likely to be positive for ctDNA, not necessarily from the actual brain, but just because of the extent of the tumor, probably. Anyway, very significant. And when we looked at EGFR at baseline, if you just dichotomize it, which is what we've been doing, we didn't see any association with survival. But as a continuous variable, we did see that improved outcomes with those with lower baseline levels, which we presume to be a prognostic effect of shedding. So in summary, we found that treatment-induced changes in ctDNA kinetics at that 8-week time point was highly predictive of long-term benefit. And this can be demonstrated in chemotherapy and immunotherapy in studies that have more recently been reported. But we found it to be more predictive than RECIST. In targeted therapy, you may only need to track the one driver. But if you're doing IO or anything where you don't have a single driver, you're probably better off using an algorithm or a consensus approach. And the therapeutic implications are that we can use this information to intercede in these patients that are not going to do well, because we can determine as early as 4 or 5 or 6 weeks whether their plasma is clearing or not. And I'm happy to say that we're actually doing this in the lung committee, where we'll be launching, hopefully this year, but possibly early next year, studies where we will actually alter therapy based on the CTD kinetics as measured at an early time point. So it's always nice when SWOG kind of gets to push the envelope a little bit on that type of study. And with that, I thank you very much for your attention, and apologize for going over time. And of course, we need to thank all the people who are involved, past and present chairs, Fred Hirsch and Ignacio Gustu, and our wonderful statisticians, and of course, all the patients and hardworking, well, I guess they don't get their recognition, but there should be another bullet down there thanking all of our patients and all of the CRAs and data protocol coordinators who do all of the hard work. So thank you very much to them.
Thank you, Phil. It's great, great use of translational medicine. ctDNA is obviously very hot these days. Any questions from the audience?
Hey there, thank you. AJ Piper Malolo. Leahy Hospital. Just a couple of questions, really exciting work. The first being, how did you document clearance? Like from a technical perspective, was it with ddPCR, just like kind of standard? And then second, did you see any like co-mutation status that seemed to predict worse prognosis at baseline? Thank you.
So yes and no are the basic answers to the questions, but I can't give basic answers. So we did this using gardens. So we were very fortunate, even at this, 8 years ago when we were formulating this this study, this concept of ctDNA kinetics was not really well considered at the time, and I was very eager to try it. And Garden was a fantastic partner. So we're doing this with Garden with their 360 analysis. And again, we tried their algorithm, which worked great, but even better was just following the EGFR mutation itself. In terms of whether there were other co-mutations that we're always on the hunt for things that could increase predictiveness, but there was nothing that we actually saw. In fact, a lot of the things that I suspected to be associated with a poorer outcome turned out to be CHIP. There's some very interesting findings, but we were able to potentially identify a few factors, including MET amplification at baseline, that were associated with a poor response. But nothing that kind of jumped out beyond that. And of course, when you start to subgroup to that low level, we only have 1 or 2 or 3 patients of any individual marker, so we can't really be conclusive about it, but there was a lot of intriguing information. It was a good question.
Thank you, Dr. Mack. This is Rafi Nakash from the Stephenson Cancer Center. So in my practice, I do tend to do liquid biopsies for monitoring for EGFR patients. But in your data set, have you seen any correlation with intracranial responses or recurrence?
I'm sorry, with?
Intracranial response or recurrence or lag time between an MRI and what you see on the ctDNA?
Nothing that came out in primary analysis, although it's a great question. The only thing that we really were able to ascertain is that if there is a presence of brain mets, you had an increased detection at baseline, which again may not be the actual brain mets contributing to ctDNA, but just the status of the tumor that leads to brain mets. Whether they had any outcome differences based on their presence or not, or any clearance differences, I don't recall that we saw any.
Dr. Mack, excellent work. Just one question. When you showed the difference with the Asian population with the paclitaxel, do you normally look at all these data sets and kind of look at racial differences to see, explain some of the differences in onset or survival? Actually,
in a casual way, yes. We always include ethnicity in all of our studies, and we're very interested in that. But to the depth that we did in that study, no, that was just limited to that study where we're actually looking at polymorphisms. In fact, it was very difficult actually to even do that without causing an international incident because both in the US and particularly in Japan, people are very sensitive about germline variation. So that is not something that we do routinely, but it is something that I think is very interesting as long as it's approached with the appropriate caution.
Other questions? Phil, I'm fascinated by the fact that RAS mutations differ and it's uniform.
Okay, so in that study,
नहीं जाना जा सकते हैं Hello.
really in a position to have KRAS mutations. But one of the built-in hypotheses was that within the adenocarcinoma subgroup, if we looked specifically at both EGFR and KRAS, we would identify like maybe a small group that is getting some benefit, the KRAS wild types. And we just did not see that whatsoever, which is in stark contrast, of course, to colorectal cancer. And none of the cases here were supposed to be EGFR mutant. Those were not involved in this particular trial. They get TKIs. So we're just looking at EGFR amplification, EGFR FISH positivity, and KRAS, and we saw nothing that would be predictive. I'm fascinated by it too.
And- I'm sorry, somehow we're having some leakage of folks from the outside. Last question, on every lung trial going forward, I assume you're doing studies at baseline and somewhere down the line?
In every lung study going forward, to the best of my ability to make it happen, we incorporate liquid biopsies, whether we have a baseline hypothesis for them or not. We routinely collect it. We spent a lot of time in early days in SWOG working with all of the sites to get them into a position where they could spin EDTA tubes and get us the plasma. I mean, many community sites, for instance, may not have had a centrifuge at the time, let alone the right freezers. And so we really worked hard to make that happen so that we can incorporate it into a lot of our studies. Nowadays, we just use preservative tubes, Streck tubes, which are more expensive, but much easier to deal with. And to the degree that we can incorporate it into everything, we are. Which is not to say we don't have clear hypotheses in most cases about what we're going to do with it, but we will collect it regardless.
So it's the old paradigm that if you have the tissue, you'll figure something out later on.
Yes, although I think I made a case that we attempt to be really prospective about it.
Well, minimally invasive, we do have hypotheses, but look at the knowledge that you gain by having that.
Right, just being able to wrestle that into that trial, which was not an easy thing to do, to be honest, but well worthwhile, I think.
Yes. Any last question? And I don't see any questions in the chat box other than everybody who's on Zoom, mute yourselves so we don't hear you somehow slipping through. So Phil, thank you very much.
Thank you.
Appreciate your Okay, our third speaker in the TM plenary session is Aaron Cohn. I became interested in AI because I know nothing about it. And I figured the best way for me to learn about it is to have somebody come here and speak about it. Neil Miracle, a very close friend of many of ours here, had moved to Flatiron a few years ago, and I asked him who would be the best speaker. And without hesitation, he said Aaron. So no pressure, Aaron. We look forward to hearing a great overview of AI and how we can use this in our prospective or retrospective analyses of SWOG trials. Thank you.
Thank you so much, Lee, and the organizers for the opportunity to be here today. I'll leave this up for a little longer than 0.6 seconds. So I'm a general solid tumor oncologist. I have the opportunity to see patients at Bellevue Hospital in New York City, which is pictured here. It's actually a really beautiful building if you've never had the chance to see it. But I also have the opportunity to work at Flatiron Health, which is a health tech company. And you can see it's a very different environment. I get to wear a t-shirt to work there. That's not the case at Bellevue. But I'd say the main way that it's different is that a lot of my work at Flatiron entails working directly with software engineers to think about how across our EHR network of over 3 million patients with cancer, how can we use technology and specifically artificial intelligence to take advantage of that scale and accelerate research that can benefit patients with cancer. And I really value and appreciate the opportunity to work in these two very different settings. And as a recent example of that, of how one informs the other, I was in clinic seeing patients and I received this email about a trial that was enrolling patients with sarcoma. And I would say that this is probably one of the main ways that clinicians at Bellevue find out about clinical trial opportunities. And we don't have a huge clinical research team. And I wanted to know if any of my patients in my panel, if I have a couple with sarcoma, might be good candidates for this trial. And thinking about the steps that I had to do, I had to remember who those patients were. I had to look them up in the EHR. I had to manually review their charts to see if any would be a good candidate. And after all that work, none of them actually ended up being trial candidates. And it took a lot of time, and I wish it had been faster, and I wish it had been easier. and I think that it can be. So let's talk a little bit more about that. Now, there's been increasing interest and money pouring into the AI and healthcare space. $10 billion was invested in AI health tech companies alone in 2021. This trend is only continuing. I'm sure many of you are aware of it. And it's because of this trend that I truly believe, as clinicians and as the teams that are caring for patients that are going on studies, that we need to know enough about these technologies to make sure that they actually work for us and help our patients. And so I have a couple goals for today's talk. I want to talk about what we even mean by artificial intelligence. I want to talk about some of the opportunities for AI in the clinical trial space, focusing specifically on helping enroll patients. And then I want to touch on some of the challenges, as well as some of the things we might be able to do to overcome those challenges. So let's get on the same page with what we even mean when we say AI. You can see this diagram here on the slide with artificial intelligence being an entire field of study. And then you have subtypes of AI, machine learning and natural language processing within it. And artificial intelligence is basically a computer's ability to perform tasks that normally require human intelligence. So I want to come back to a specific example of this in a second, so hold that thought. Machine learning is a subtype of artificial intelligence that uses statistical techniques that allows a computer to learn without being explicitly programmed to do that. And we heard earlier in the excellent talk by Dr. Blemman an example of machine learning, where a computer learned to recognize patterns in cells so that it could classify them into TILs. And there's a lot of different types of machine learning, but the point I'd like to make is that if you have enough data, and that data is high quality, then computers can learn to perform tasks really well. And that data could be pathology, it could be images, it could be rashes, but it also could be language. Which brings me to natural language processing. And this is an ability of a computer to derive meaning from and make use of human language. And this is actually really challenging because the computer needs to learn to understand our language. It needs to understand grammar, relations, negations. And so it's difficult, but it's also really promising when you think about how many important clinical details are written in an unstructured way in the EHR. And so I promised an example a couple slides ago. Let's come back to an example of AI, which is a computer's ability to perform a task that normally requires human intelligence. So meet GPT-2, the AI robot that can auto-complete your thoughts. And at a high level, GPT-2 is a machine learning model that's been trained on a lot of data, except in this case, that data is language, to be able to predict what you want to say. And they have this unicorn on their website as the avatar for this program. I like to pretend that that's who I'm interacting with. And as I was preparing for this talk and putting it together, I was thinking, this is a lot of work and this is a lot of pressure to give a talk on how AI can help clinical trials to a bunch of clinical trialists. I should really ask AI for help. And so I did. I prompted the unicorn with the following statement. I'm giving a talk on the ways that AI can help clinical trials. The number one way is by. I'm going to show you 3 of my favorite responses from the unicorn. Okay, the first, the number one way is by identifying people who are likely to have a particular condition so that we can help those people more effectively. That's pretty much what I'm talking about today, so well done, GPT-2. Second, recognizing what a patient would want or need during clinical trials. I think that makes a lot of sense as well. Which patients are at risk of dropping off study, which might have adverse events. And last, and my favorite, I'm giving a talk on AI to help clinical trials. The number one way is by improving this talk. I kid you not, that was the first response that GPT-2 gave me. It didn't exactly, to your point, Lee, help my stress level. And I put the link here if you want to play around with this. And it's a fun example. There's actually a newer version of this now, GPT-3, that's learned on even more language. I don't even want to think how snarky that model would be. But hopefully this is beginning to get you guys to think about how you could use artificial intelligence, and specifically machine learning and natural language processing together to make predictions based on text. Remember, how many clinical details are in the text of the EHR? Could such a tool tell me if any of my patients with sarcoma are a good candidate for that trial? And so, as I've said, there's a lot of opportunity for AI in the clinical trial space, ranging from data management, so reducing redundant information and errors, to informing site selection, so knowing where the patients you're interested in enrolling are actually being seen, to monitoring them better for adverse events, as we talked about. So there's a lot, but in the time that we have today, what I want to focus on is how you can use AI to more efficiently surface patients. Because if you can do that, that unlocks a lot of these things, including more efficiently enrolling patients on clinical trials. As we've talked about, there's so many clinical details in an unstructured format in the EHR. This is where the inclusion criteria for clinical trials lives. This is what I had to manually review when I was seeing if any of those patients would be candidates for that sarcoma trial. And we know that no matter how hard we try to get clinicians like myself to enter this information in a structured format because it's more usable, that it just doesn't mesh with our clinical workflow. And so it would be really nice and promising if there was some way, an automated way, to pull these details out of this unstructured text to help us with that. And so what I'd like to do now is walk you through how we can actually do that, how we would build a model to pull details out in an automated way with the example of metastatic status, which is obviously a very common inclusion criteria for trials. So I'm going to walk you through the steps of how this would work. The first thing that we would do is identify a list of relevant search terms. And the idea behind coming up with these search terms is that these should be terms so that if the computer found these words in the text of the patient's chart, and then looked at the text around those terms, or the snippets of text, we ideally would be able to figure out whether the patient's metastatic or not. And you see a list of terms here, METs, stage, et cetera. It's not an exhaustive list. And let's pretend that this is the patient's chart. So what the computer would do is find these words in the text of the chart, which we see here. And then the computer would look at the snippets of text around these words. It could be a couple sentences before and after. It could be a couple words before and after. For this example, we'll look one word before and after. I think I went 2 slides, or maybe I didn't. No, okay. And the result of this are phrases or features like bone mets and stage 4. And what we can do is take these phrases or features and assign the number 1 to those phrases or features that are consistent with having metastatic disease, and 0 if it's not. And then we can take these features and use them to train a logistic regression model, where the model will learn to associate weights with these features. And ideally, the model learns to give high weights to phrases like stage 4 and bone mets because they're correlated with having metastatic disease. And remember, all of this is happening on examples where we know the patient's metastatic status. It's labeled data. But the promising thing here is then you can take that model and the weights that it's learned and apply it to examples where you don't know the metastatic status, and therefore be able to make predictions on a patient, whether a patient's metastatic or not. So that's how this works, but let's take a look at how a model or tool like this would actually be used in action. So this is OncoTrials. This is a tool we use at Flatiron. And what it is, it's a tool we use to match patients to clinical trials. And how it works is we use these AI tools to make predictions across the patient's chart on a number of clinical factors, including metastatic status, but other things as well, like biomarker results. And then we can take the results of these predictions and use them to match them to the eligibility criteria of trials. And so in this example here, which hopefully you can, you're on the right slide now. So in this example here, you can see in the middle that there's a patient with breast cancer that's been predicted by the model as being very likely of having metastatic disease. And so what we can do then is preferentially surface trials, and that's what's on the right side of the screen, to a clinical research coordinator for which metastatic status is an eligibility criteria. And importantly, not only can we preferentially surface the trials for which the eligibility criteria match, but we can also hide trials for which metastatic status is not an eligibility criteria, such as in the early disease space. And it's in doing this that we can provide the clinical research coordinator with patients that are more likely to be matches for certain trials, so that he or she can spend more time thinking about patients and trials that are likely to be matches, and less time thinking about patients and trials that are unlikely to be matches. So this is something that we've published on in the citations here if you want to take a look. But something else that's really important for me to get across to you is it's not like these models are performing autonomously without any human involvement. And in fact, humans have been involved in this process at a lot of different points. From defining what the problem is that we want to solve, to training the tool, to evaluating the model, to making sure that it's good enough for a given use case. And in this case, the model performs really well with a sensitivity of 95%, meaning of all patients with metastatic disease, the model finds 95% of those cases. And a positive predictive value of 90%, meaning that when the model says the patient's metastatic, it's right 90% of the time. People have been involved with integrating this in the clinical workflow to make sure that it actually works for clinicians, it actually works for clinical research coordinators. And probably most importantly, it's still people that are making the final decisions here. And so this isn't, a clinician still needs to confirm a patient's metastatic status. A clinical research coordinator still needs to review the eligibility criteria and ultimately enroll that patient on study. None of that's being replaced. The hope is that it's just being made more efficient. So this is an example of, we have a patient in front of us. Is there a trial that matches that patient? But let's consider a slightly different example where we have a trial, let's say enrolling patients with rare cancer types, and we want to know if there's any patients out there who might be good candidates for that trial. So at Flatiron, we've been involved in a study for patients with blastic plasmacytoid dendritic cell neoplasm. This is a really rare type of hematologic malignancy with approximately 1,000 to 1,200 cases a year across the United States and Europe. So you can imagine the challenges of enrolling such a study. And what we've been able to do is build an AI tool to help surface patients across our network that might have a new diagnosis of this disease. And of course, because new diagnoses happen all the time, over time, we're able to do this in a recurrent way to capture new diagnoses over time. And so over the course of the last year, we've managed to find around 65 patients that might have a new diagnosis of BPDCN. And then we've been able to perform manual chart review to confirm that 6 of these cases actually do have BPDCN, a new diagnosis, and had yet to start first-line treatment. And as a result, might be eligible for a first-line investigational clinical study. And then we've been able to reach out to the participating sites where these patients are being seen and make the clinician and the sites aware of this trial in hopes of perhaps giving the patient an opportunity to participate in this trial. And so I think this is a really unique and interesting application of using AI to service patients with a rare cancer and giving them an opportunity to participate in a trial that may not have happened otherwise. So those are some of the promising applications for AI in clinical trials, but let's think about some of the challenges now, because there are some. And I'll start by talking about data. You've heard me talk about the importance of having lots of data, high quality labeled data to train these models. And that is key. And it's something that we've been able to take advantage of at Flatiron, but I realize this isn't always going to be the case, and it can be especially hard for rare diseases or rare events. And this also speaks to the challenge of interoperability when we have all these different health systems and EHRs that don't talk to themselves. Kind of related to this is generalizability and fairness. So how are these tools actually going to work in the population that you're using them in? Are they going to work fairly? Will there be biases? Will they work differently in different subgroups, such as patients of different ages or genders or races? These are really important things to tease out and understand. Integration into the clinical workflow. You heard me talk a little bit about this in the onco trials example, but you could train the best performing model, and it doesn't really matter if a clinician doesn't trust it, doesn't want to use it, doesn't know how to use it. Regulatory. The FDA has been doing a lot of thinking about this, including putting out guidance for clinical decision support and guiding principles for AI software as a medical device. And I'd say that this is still very much evolving, particularly in the field of clinical trials. Explainability. How do these models work? It's one of the things that I actually hope makes a little bit more sense to you all after this talk, but this is still an issue, particularly for some of these really complicated neural networks that are described as black boxes, where even the programmer may not be aware of how it's making predictions. At Flatiron, we've tried to overcome some of these challenges. This is a paper we published early in the year, which is a performance evaluation framework for thinking about how to methodically evaluate how a model performs when it's pulling clinical details out of the EHR. And the idea behind this is that it's not enough simply to understand the overall performance metrics of a model, but you also need to understand how it performs in subgroups of interest to make sure there is no bias. And additionally, it's helpful to know the errors that these models are making and what impact those errors may be having on your results or downstream use cases. And the hope is that by being transparent and methodical about how these models are working and performing, that helps build trust. But what I'd like to finish talking about, which I think is arguably the most important piece here to address some of these challenges, is the importance of communication, and specifically cross-functional communication. To share a quick example, our team at Flatiron developed a tool to predict PD-L1 details on patients with non-small cell lung cancer. So whether they were tested for PD-L1, what the result was in these different expression categories, what the result date was, it performs really well. We're very proud of it. And one of our really talented software engineers took this work and decided that he wanted to try to apply it in different cancer types. And so he did a couple weeks of modeling and prototyping. And after that period of time, he just really wasn't understanding the results he was getting. They weren't as good as he thought they should be, and he just didn't know why. And so he and I finally had an opportunity to sit down together, and we were talking about it. And what I ended up explaining to him is that in the non-small cell lung cancer example, our models had learned that tumor proportion score is the relevant result. And then obviously these are the relevant expression categories, less than 1, 1 to 49, greater than equal to 50. But when you branch out to other cancer types, that's not always the case. And in fact, combined positive score is often relevant with very different categories entirely. And of course, there's no way that he could have known that. We have very different backgrounds. He's a software engineer that was trying to explain model architecture to me and feature engineering, and I'm a clinician trying to explain clinical concepts like, yes, there's a TPS and a CPS, and they're different, and that's why things don't look right. And it's a simple example, but it's important because it's often like we're speaking different languages. But as I said, it is so important to have that cross-functional communication. Think about it. There is no one else out there who understands clinical trials, how they're done, what they need, what our patients need from them, more than you guys. Imagine taking that knowledge with openness and patience and bringing it to work with software engineers. The very software engineers that are probably on the same campus as you, and they may be working a couple buildings away, and bringing that knowledge to work with them to solve these problems. That is the way we're really going to build tools that help our patients. That is the way that we can start to learn to speak the same language. And that is my challenge to all of you today and going forward. So thank you so much.
Thank you, Aaron. You did a great job of simplifying it, yet it's still very complex. So, let me, if there are any questions, please come up to the microphone. In the meantime, there are a couple questions and comments in the chat box. We have about 125 people who are attending remotely. I may have missed it. I may have missed it. What will create the database of clinical trials with the relevant disease sites, stage, etc. of the eligibility? Can AI abstract info from clinicaltrials.gov?
Yeah, that's a great question. In the OncoTrials example, so we take clinical trials that are relevant to a given site and upload them so that they can be matched to these predictions that we're having. The question about whether you can use AI on data that's been collected for clinical trials is, I think, a very promising application of AI, because what really matters when you're training these models is high quality labeled data. And you could argue that there's no better example or situation for getting that high quality labeled data than the data that's collected from clinical trials. I think that was the question, but.
Well, I think it was more about, how do you pull, clinicaltrials.gov is a mix. You go on there, you have some great information, and you can't figure out what's going on, and you don't always get the trials you want. So with clinicaltrials.gov being a wonderful resource that we didn't have years ago, but not being entirely clean, do we need to provide clinicaltrials.gov or the leadership with a template? Or do they need to develop a template which would interact with AI?
Got it. The short answer is yes. The better you can standardize how things look, the better a pattern can be recognized by these tools. And one of the challenges when we're training models is all the different standards and documentations. You think about all the different PDF reports for different NGS vendors out there and how different they look. It makes it hard, it makes it messier. And so the more standard and templated that things can be, the better that these tools can work.
So I'm going to start 1, 2, 3, 4. So
Okay.
let's start
These
over
lights
there.
are so bright.
Can't
but-
see that far, but let's start over there.
Thank you.
Center. I was just wondering, while you were talking, if you thought about, maybe this goes under the regulatory concern, but like how you would deal with patient privacy in this situation. I think ideally you'd probably want not to have a different model within each institution where everyone's kind of, signed a confidentiality agreement essentially, but I would be concerned about who's getting access to all of those raw, electronic health records, or how you would deal with that.
Yeah, privacy is obviously extremely important. So at Flatiron, we have business associate agreements with their sites where patients are being seen, and we have an IRB to do a lot of this work. But thinking about how this would extend to other sites, it's certainly something that needs to be prioritized. It's certainly something that you need, I would say, good governance over. And I know that the FDA is thinking about that, not only that these models perform fairly, but that they ensure privacy. So it is something that I would say requires a lot of thought going forward. Thanks.
So, Aaron, I'm Ian Kropp at Yale. Great presentation. And I think having a highly effective clinical trial matching software system is kind of the holy grail for all of our cancer centers. What needs to happen for these to become these types of approaches being widely available and working well so that we can use them kind of universally for our screening patients? I mean, I think it's something we desperately need. And we've heard lots of talks about these kinds of things. What's the breakthrough that needs to happen so that they're now available?
Yeah, it's a tough question. I think there's a couple parts to it. The first is making sure that you would have these tools that work well enough to be helpful. And so how can you train a model on enough information that is relevant and generalizable across all of these studies? I think you saw in our example with OncoTrials, what we're training on is our network. It's not clear how that would work for clinicaltrials.gov or another site. And so interoperability, training on lots of data, figuring out a way to monitor performance, because it's not always going to be possible to train on each of these additional sites. You may end up using a model developed someplace and applying it somewhere else. And you just need to be really careful when you do that and monitor performance and make sure that it's performing as intended. The other point I would say related to how I ended is that I think clinicians being involved in the development of these tools and really sharing what would work for them and what's important for them is going to be key. Thanks.
Junaid from University of Arizona. Thank you very much for a very interesting talk. My question is related to the healthcare disparities. How do you think artificial intelligence would impact the issue of healthcare disparities? This is especially important from the aspect of clinical trial enrollment as well.
Yeah, I think there's a couple different ways. The FDA has been, I think, very clear about the importance of diversity plans going forward. They have some draft guidance out from there, and you can envision using these tools to help perhaps surface patients that may not have had the opportunity to participate in trials previously, have a better shot at doing that. I think another thing that comes to mind is when you think about race information and ethnicity information in the EHR, it's not as complete or accurate as we would like to think that it is. And oftentimes it's the basis for all the disparity outcomes research that we do. And so really thinking critically about what is the status quo, like what do we have right now and how can it be improved? Can missingness be improved with some of these tools? How things are being documented in a structured format, is that the patient's actual race, or is it actually better categorized in an unstructured way, someone in the note? Or how will you reconcile those differences? And so it's something we're thinking about a lot at Flatiron. It's a great question and is certainly important.
Again, Anthony Elias from Colorado. Great topic. I mean, one of the ways, of course, to use this is to integrate it with the electronic medical record, because then you solve the problem of just picking out my patients and I search within my patients, then you don't have privacy problems, etc., and linking it to clinicaltrials.gov and for the trials that are open in a certain location and so forth. So there's a lot of things that one can pull into the medical record, but ultimately sending the patient's records outside might be a problem, because that's when you start getting concerns about privacy and who gets to see this. Are there plans to put search engines within the medical record, like Epic, for example?
Yeah, I think that's a great question. I think that there's a lot of obviously promising things that can come with doing something like that with search records. To my knowledge, I'm not familiar right now with any efforts to do that. It's a great question. I'd have to think a little bit more about that. No. Sure.
I had worked on Watson for Mayo Clinic for PTM at some of the same work presented. But the question which the answer you may have alluded to is that when a radiologist is trained to read a CT scan, and a CT scan is done on a GE machine or a Panasonic or a Sony, a radiologist can still read the CT as a CT. But I think what you said was that a software trained on Flatiron would not work on Epic or Cerner, is that right? So we would then need validated softwares for Epic, Cerner, or Flatiron, or XYZ softwares.
So Epic, we do at Flatiron, we do integrate with Epic, and so it's really a combination of two EMRs, EHRs, OncoEMR and Epic. I think that I think what you're asking and what I'll say is that these models really work best, and we understand how they work when you're applying them, you're deploying them on the same populations that they were trained off of. Is that what you're kind of
Yeah,
getting?
exactly. So what I was coming to is that one software would then not work across and would then need to be validated against each EMR. So
Yeah.
the second question is that how close you are to read the PDFs, right, for NLP, because that's where our biggest hurdle was at Mayo Clinic, where it would not just read the NGS reports, and because many of the trials are precision medicine trials, and also the lines of therapy, which is nuanced for each tumor. It would read metastases very well, stage 2, 3, 4, but would then get confused in lines of therapy.
Yeah, so these tools are reading the PDFs. They're using optical character recognition. Their success can vary based off of the quality of those PDFs, certainly. But when I present how these tools work and where we're getting these PD-L1 predictions, for instance, that's coming from a combination of clinician notes as well as PDF reports.
And the sequence of therapies.
And so sequence of therapies is interesting. We rely a lot on structured data for IV therapies when thinking about lines of therapies and sequences, but you can't really rely on that for oral data, oral treatments, because they're infrequently documented that way. They're usually free texted. And so we've been experimenting and have actually developed I would say, form of line of therapy that incorporates structured data as well as ML extracted data for orals to sequence treatments.
Thank you. So let's have 2 quick questions, 2 quick answers, then we're going to have to close the program. So first question.
Thank you. So I guess my question was partly what Parminder was asking about NLP and PDFs. So if you're working on a small project, so definitely can't compare with Flatiron and what you guys are doing, but have you guys been able to build a database for the nomenclatures by any chance? Like, the difficulty, let's say, in our pilot project that we're having is adenocarcinoma for lung, then there's different types of histologies for, have you been able to build that or integrate that yet? Or is it something that you plan to do?
Yeah, so we've actually built an entire data model for non-small cell lung cancer using only structured data and ML extracted variables. And so we've built models to extract the diagnosis of non-small cell lung cancer, yes, no, and the date, advanced status and metastatic status, yes, no, and the date, histology, biomarker results and dates, orals and dates. I already kind of summarized PD-L1 for you. So we have what we think surgery, we have what we think are the key details and variables that you would need to answer outcomes research questions on patients with non-small cell lung cancer, just using AI tools and structured data.
Last question.
Tim Robinson, Yale. Great talk. So you talked a lot about identifying patients that were eligible for trials, but sometimes you have a situation where you can find those patients, maybe early stage breast cancer, but a bigger question is which one of those will actually go through and participate on the trial. Have you guys done any work, understanding it could be a can of worms, of trying to identify patients that are high likely to actually participate in the trial?
Yeah, that's such a great question. We have some information and data on that from onco trials. But in the example of the blastic plasmacytoid dendritic cell neoplasm, where obviously you'd argue that it's one thing to raise awareness, it's another thing to actually see that those patients got enrolled in the study. Kind of the limits of how that study was set up and what we were allowed to do was that it was really an awareness raising study. We weren't allowed to go back in the charts and kind of survey whether that patient actually ended up on study. And so to your point, I think that's a gap that needs to be followed up on, because it's one thing to kind of surface patients, to your point, it's another thing to actually get the results that you want. Yeah.
So Aaron, thank you. I think we've learned a lot and we have a lot to learn. So I think having a workshop at the next meeting may be informative and more one-on-one discussions. There are a couple questions here. I'm just going to ask one quick question to make sure that we engage the people out in Zoom land here. On the front end, can registry be used to prioritize the studies that might be more useful for specific demographics? We activate a lot of studies with minimal accrual. So how do we move? protocols up on the list, which are having hard times, which are having a hard time finding patients that can enroll in those trials.
Yeah, so, thinking about how you might use AI tools to better prioritize it or deprioritize studies and trials is interesting. And I think where you could start is, are you going to have enough patients to enroll this study? Are you going to have enough of the event that you're interested in to actually be successful with the study? So I do think that AI tools are actually a good application for that.
And then the last question, or the last principle, is that humans are not perfect and make mistakes. How do you train humans to use the EHR better? This is a big issue, so that they don't spend a lot of time. I wish my PA were here to talk about, putting data into the EHR. And how do you train humans how to work with and anticipate the needs of the AI to find your endpoint or whatever you're looking for? I mean, this requires more EPIC training, as if we want to spend more time on EPIC training, et cetera. So you're kind of like up against the wall. You win it, How do you address that issue of the accuracy of the input of the data?
So a couple thoughts. For things that are relatively easy for a clinician or whoever to enter in a structured format, please do that. I spend way longer on my charts than probably most people, because I know that if I enter a patient's diagnosis and date and stage and ECOG performance status, that even though it's not me who's going to be using that data, it's really helpful. When it becomes time for thinking about how to standardize how unstructured data entry can be used, I think the best thing I can say is that we can train a tool or create a tool to do anything that humans can do well. And so if you were imagining that you were the one going into the chart and you had to try to pull something out, what would be the easiest way for you to do that? If you wanted to know if a patient had non-small cell lung cancer and what the diagnosis was, it'd be nice if that always showed up in like the first sentence of your HPI or in the impression and plan, and it was consistent and predictable where that was going to be. Obviously, everyone has different documentation patterns. There's no way that that's going to be solved anytime soon. But if you're asking what one person could do or how we can train people to start thinking about this to help AI tools going forward, I think it's, are you as a human going to be able to pull this information out how you've documented it? Then chances are a tool can too.
So I want to end on a ridiculous statement that you're not allowed to reply to.
Okay.
How do we make the EHR simpler, more of a template, and easier for everybody to use so that everybody benefits? And maybe you'll come back next time with an answer, because all I hear and read about on Twitter and everything is how much people, I'm going to use my words carefully, are not in favor or are not in love with our current EHRs and don't feel that it's accurate. And the data that comes out of the AI analysis is only going to be as good as the data that comes into it. So think about how to fix the entire system and then come back to us next time. I think we thank Aaron and all the speakers for outstanding and diverse presentations. We thank the Hope Foundation for supporting so much of this.
Thank you.
And we'll see you all at Dr. Blanky's Plenary II session tomorrow afternoon. Thank you all.